In this video, we are going to begin our study of more complex probability calculations, especially ones involving conditional probability. And the first tool that's going to help us start thinking about conditional probability is called marginalization, and that's what we're going to start first. So in order to think about marginalization, I'm going to draw a picture here. So in this picture, I have a sample space S, represented by this big gray rectangle. And inside this sample space, I have a bunch of sets B, pink sets B here. And these sets B are what we call a partition of the space. And the partition properties are that if I have two different sets B, they are disjoint. So there's no overlap in any of the B's. And also, if I take the union over all the possible B's that I have, what I'm going to get is the entire sample space. So these two partition properties, we actually saw them when we were looking at equivalence relations as well. Equivalence relations also partition a set into subsets with this property of mutual exclusiveness and collective exhaustiveness. They collectively create the set S. And then let's add to this a set A. So here's my set A represented by the circle, and I want to know the probability of the set A. And if we kind of look at the picture, we say, hey, I can think about the probability of set A as being composed of three pieces in this picture. So I have one piece right here. I have one piece right here. And then I have one piece right here. So what are the probabilities of these three pieces? Well, let's think of each of these pieces as intersections. So this piece up top here is A intersection B3. This piece is A intersection B4. And this piece is A intersection B2. And we can see that the sum of each of these intersections adds up to A itself. And so if I want to know the probability of A, because all of these are disjoint, I can use the disjoint addition property and say, hey, the probability of A itself is just the sum of the probability of each of these three intersection events, A and B3, or A and B4, or A and B2. And so this gives us our formula for marginalization. Here it is. If it's the case that some set B is a partition of our sample space with the partition properties we have above, then if I want to calculate the probability of any set A in my sample space, any event, then one way I can do it is by calculating the probability of A and BI, and then summing over all the possible choices of BI. So I look at the intersection of A with B1. That one is empty. That's not going to contribute anything to the sum. I compute the intersection of A and B2. That one is not empty, and so that is going to have a non-zero term here. B3 and B4, B5 and B6 are going to have zero terms again. And if I add all of these up, I add the probabilities of all these intersections, I'm going to get the probability of A itself. So I'm beginning to figure out how to calculate probabilities of events that might be complex or composed of many pieces in terms of events like this that are more detailed in some way. But oftentimes in practice, that level of specificity and detail allows us to calculate these probabilities more simply. And so if I'm able to do that more simple calculation, then I'm able to combine them in ways like this in order to get the probability of the complete event. So now we're going to develop the marginalization idea one step further using tools we've already seen before. So here's two facts that we know. So over here is the marginalization formula. I haven't stated the assumption that the BIs need to be disjoint and exhaustive, but that's okay. So here's our marginalization formula that we just introduced. And then here is our formula from a couple of videos ago. This is just a direct consequence of the definition of conditional probability. The definition of conditional probability is PA and B divided by PB. So I just multiplied out the PB to give us a formula for the probability of A intersect B. That probability is equal to PA of given B multiplied by PB. Okay, so what we're going to do is we're going to combine these things into the following theorem, which is important enough to have a name. It's called the law of total probability. Here it is. Um, the law of total probability, if I have a partition of my sample space, then the probability of A is equal to the sum of these terms here. Each term is just the same as probability of A and B. It's just these guys, but we've used this formula to break them down one more step. So I sum up all the possible choices, probability of A given BI, times the probability of BI. And all of these together give me the probability of A. So we can think about it as scenario analysis in a way. I want to know how likely A is. And so I ask myself, hey, what's the probability that I'm in scenario I? Let's think of B as a scenario here. So I ask myself, what's the probability that I'm in scenario I? And then if I'm in scenario I, or given that I'm in scenario I, what's the probability of A in that scenario? So I do this kind of scenario analysis, and then I add up across all my different scenarios, weighting them by their probabilities, and that gives me the overall or total probability of A. So let's do an example that comes up a lot in communication theory and information theory. So oftentimes we need to transmit a signal over some kind of channel. So the channel might be electrical, it might be radio waves. There's a lot of different ways to communicate a signal, but no method of communicating a signal is perfect. I'm always subject to errors. And so how reliable is my communication given the presence of errors is a very important topic in electrical engineering. Let's do a simple example here. I have two people. I'm going to call them Nia and Alvaro. And Nia is going to send Alvaro a single bit, a 0 or a 1, through a noisy channel that sometimes corrupts the data. So, in other words, if Nia really truly sends a 0, sometimes, maybe not often, but sometimes Alvaro might receive a 1 because the channel corrupted the signal. So let's make this a little bit more concrete. So let's say we have a probability that Alvaro receives a 1, given that Nia sends a 1. Let's say that's equal to 0.8. And the probability that Alvaro receives a 0, given that Nia sent a 0, is 0.7. So this is not what we call necessarily fully symmetric channel. So this channel treats ones and zeros a little bit differently, but they both have a probability of being corrupted. This means that if we kind of do our complement rules here, so the probability that we get a 0 received, given that Nia transmitted a 1, well, it has to be 1 minus this, because I'm in the 1 scenario, so those are my only two possibilities. So we need to do 0.2, and then the probability that there's a 1 received, given that Alvaro sent a 0, is equal to 0.3. Okay, so this is our channel. It has some noise to it, so it can corrupt your data. If you send a 1, if Nia sends a 1 to Alvaro, the probability he actually gets a 1 is only 80%. He might also, by a corrupted noise, he might also get a 0 with probability 20%. And similarly for the case that Nia sends a 0. So what we want to know, for starters, let's just ask ourselves, hey, what's the probability that Alvaro receives a 1 from Nia. And for this, we need one more piece of information. We need to know how often Nia wants to send Alvaro a 1. So suppose that Nia sends Alvaro a 1 with probability 60%. So she wakes up in the morning and 3 days out of 5, she decides, okay, I'd like to send Alvaro a 1 today. So what's the probability that Alvaro actually receives a 1? Let's see if we can figure that out with the law of total probability. So the probability that Alvaro receives a 1 is equal, by the law of total probability, to the probability that Alvaro receives a 1 in the scenario that Nia sends a 1 times the probability of that scenario, plus the probability that Alvaro receives a 1 in the scenario that Nia actually sent a 0 times the probability that Nia sends a 0. So let's see if we can now figure out what these are. Let's remember that the probability of 0, Nia sending a 0, is just 1 minus the probability of Nia sending a 1. So that's going to let us fill that in. So here we go. We have probability of 1 received given that Nia sent a 1. That's 0.8. And then we're going to multiply that times the probability that Nia actually sent a 1, which is 0.6. Plus, okay, the probability that a 1 is received given that Nia sent a 0 is 0.3. And then the probability that Nia actually sent a 0 is 1 minus the probability that she sent a 1, which is 0. So now if we go ahead and finish our calculation here, okay, so the 8 times 0.6 should be 0.48, and the 0.3 times 0.4 should be 0.12 equals 0.6. So kind of by coincidence, this is not always guaranteed to happen, but kind of by coincidence with these specific numbers, we found that the probability that the 1 is received is actually equal to the probability that Nia chooses to send the 1, although this won't always be the case. With different kinds of noise, different values here, for example, we could have gotten a different answer here. So this is an example of how we can start using the law of total probability to compute the probability of an event when we have little individual pieces. So I wanted to know the probability that Alvaro would receive a 1. I didn't really have that, but I had these little individual pieces here, how much Nia wants to send a 1 on a given day, and what the probability is that Alvaro receives the 1 given that Nia sends it. So I sort of have these little mechanical pieces that I get often by reasoning about the structure of my system in some way, knowing how reliable a given channel is. And then I combine those pieces together using rules like the law of total probability in order to compute the probability I care about.